Hello, everyone. So my name is Árpád Rózsás. I'm from TNO, and in line with the previous presentation, this presentation will also focus more on the application, the practical application side, and more on the engineering parts. And I would like to show the engineering framework, the motivation, the problem in which we have embedded the structural reliability problems. So briefly, the motivation that in industrially advanced countries in general, the built infrastructure comprises about 50% or even larger percentage of the national wealth. So it's uttermost important to take care of this infrastructure. And an additional point is that this infrastructure is aging rapidly. In these countries, in OECD, industrially advanced countries, the infrastructure was built during the 50s. So many structures from the infrastructure are reaching the end of their design life. And then also we have a lot of uncertainties related to material properties, but even larger uncertainties concerning the loads. And then given this motivation, the aim or the engineering challenge is to gain a better understanding of what is going on with these structures, somehow reduce uncertainty, for example, by doing structural health monitoring, doing some in situ testing, gathering data, and then use this information maybe through reliability assessment to extend the lifetime of structures, but in general to achieve a more economical asset management. So the engineering problem statement is here. So we have given this extremely valuable asset, built infrastructure, and it's aging. So the maintenance is a big question. It's an economical question. And then given the current practice, and now when I'm saying current practice, I'm referring to the current practice in engineering, in practice. The methods we have, the semi-probabilistic methods which are offered in standards and guidelines, are almost exclusively for existing structures. So there are these questions: what to do with for new structures, and then what to do with existing structures, what to do when we observe some deterioration, some corrosion, then how to evaluate the compliance of the structure. Often the case is the following, that if we just do a Eurocode-based analysis, we find that the structure doesn't comply, and then we have to make a decision whether strengthening is needed or not. And then structural reliability methods and advanced nonlinear finite element methods could offer a solution how to basically save costly maintenance. So this little table or matrix is showing these two dimensions. One here is using more advanced mechanical representation, physical models for our structures, and the other dimension is to use more advanced, more sophisticated, hopefully more realistic probabilistic representation of material properties and actions. So I put here the current state of practice. So generally we use simplified mechanical models. Even if we rely on finite element models, we usually use linear finite element analysis. So one way to extend and to explore hidden safety or some reserves of the structure is to utilize the nonlinear capacity of the structure. So this can be done by using nonlinear finite element analysis now. It's the computational power, the software packages are available to achieve this. And the other direction is to use more sophisticated probabilistic representation. So instead of relying solely on semi-probabilistic methods and partial factors, we hope that if we extend our models to the probabilistic space, if we represent our uncertainties using random variables and random fields or stochastic processes, then we can also explore and uncover some hidden safety, so we can show by direct reliability analysis that the structure still complies with the requirements. So what is shown here, that reliability analysis and comparing the reliability level of a structure to a target value, which is, let's assume that the target value is well defined and is acceptable by the society, then we can actually make a decision in respect of the structure, what to do with the structure. And then an additional advantage of using reliability analysis, that these methods, these simplified methods which are used by practitioners, and in my opinion will be used by practitioners, can be calibrated. So we can use this as a reference point and calibrate the simplified methods, and those methods could be given to the practice to actually carry out more advanced analysis. But here we have a lot of questions in respect of the reliability analysis. one issue is a computational issue, that if we want to do such a reliability analysis, the evaluation of the nonlinear finite element analysis, our complex representation of the structure, is computationally expensive. So if we plug in our nonlinear finite element model into the limit state function and we have to evaluate it a couple of thousands of times, then it often and quite quickly becomes computationally or practically intractable. And then other additional more practical questions: what is the related model uncertainty? So if we decide to build a two-dimensional finite element model, or if we go for a three-dimensional finite element model, the model uncertainties are different. And to our knowledge, these uncertainties are not quantified in the literature yet. And then these additional questions which were already raised during this day: for some actions, some material properties, random field representation seems to be desirable and needed. For example, for hydraulic structures, when soil is involved, and the soil is usually advised to be considered as with spatial variability, the strength of the soil, but also for corrosion effects. Corrosion is often advised to be considered as a random field. And then this last question is what I just mentioned here in this table: how to translate these structural reliability methods and the results to something which can be used and utilized by the practice, because it's really not expected that practicing engineers will carry out direct reliability analysis. So I just want to highlight some ongoing projects we have within our group. These will provide a focal point to this presentation. So we have an ongoing project on reinforced concrete structures, so focusing on deterioration. The aim is basically to show that if we have a corroding reinforced concrete bridge, then we cannot show basically prove that the structure complies with the standard using the standard methods, whether we can show that the reliability methods can be that the reliability methods are still showing that the structure complies. And also other project is related to hydraulic structures, where the interesting point, the challenge, is the soil structure interaction and also deterioration. For example, sheet pile walls are generally corroded, and then how to take into account the spatial variability of this corrosion. So we have a lot of both of these projects are multifaceted projects. We have multiple other aspects, but now I will just focus on the probabilistic assessment and reliability assessment component. So in both projects and in all the so far mentioned engineering challenges, the underlying mathematical problems or challenges are related to, in our opinion, to computational challenges, that if we would like to run these models in a reliability calculation, then the computational time often becomes like days or even weeks. So even for simple cases, if we have a single failure mode, no random fields, and we are not doing any kind of code calibration, so that's one of the main motivations to organize this workshop, to learn from those guys who are more into developing methods. So the focus is on how to deal with multiple failure modes, random fields, and potentially even updating the failure probability of structures based on measurement data. And the final step is code calibration. So what we see as possible pathways to reduce the computational time is to use smarter reliability algorithms. So we have heard a lot. We have seen some quite promising approaches, algorithms, how to reduce the number of limit state function evaluations. So it appears to be that even for high dimensional cases, we can calculate the failure probability with a couple of thousands of evaluations. But in some cases, this is already like too much. So very likely it's inevitable to couple it with smart computational algorithms when we can run these nonlinear finite element calculations or any kind of costly physical model evaluations in parallel. And also this other one, which is not necessarily different from a smart reliability algorithm, but it's more an engineering approach, what Sudhir mentioned many times, that we should somehow try to reduce the dimensionality of the problem, so to use the engineering insight to reduce the problem as small as possible, but still representing sufficiently the actual structure. Regarding the tools we are using within our group, we have an in-house developed tool which is called Prop2B. and if I'm not mistaken, it's based on C++. The core source code is coded in C++, but now it has a Python extension and a Python interface, so it's now coupled with OpenTurns. All the features of OpenTurns are available and accessible. We also use and rely on Ferrum, which is a MATLAB-based tool developed at Berkeley and now maintained and developed at the French Institute. And we extended and added some methods according to our needs. For example, this adaptive directional sampling method, which is a variant of the method what was already mentioned and described by Panos, so I will not go into details. That's basically the extension, the addition of our contribution to that method is we extended the response surfaces which are available. So not only considering polynomial response surfaces, but kriging as well, and introducing different kind of goodness of fit measures, so we can simultaneously consider different response surfaces which can sort of compete against each other. So during the analysis, during the sequential analysis, it can decide now a kriging model is better or a polynomial model with certain degrees or number of parameters is better. And also what we are working on or added to these methods to couple the reliability algorithms with finite element code. So for example, coupling with Diana or OpenCs. So I would like to show some examples. So these are just small examples. So these will be low-dimensional problems that they hopefully will already indicate the challenges and the problems in terms of computational demand. And then also I would like to show, probably for the practice, it will be interesting how much gain we can get from moving to more advanced mechanical representation and more advanced probabilistic representation of our problems. So this example, this deep beam, is taken from the literature just to have a reference to be compared with. So here we can see that the finite element model, which was developed in Diana, a two-dimensional finite element model using plane stress elements, embedded reinforcement with perfect bond, is apparently can capture the global behavior of this deep beam. What is important that material nonlinearity in concrete and rebars is included. And as I mentioned, the limit state function, the number of random variables are quite limited, so we have only 3 random variables. We considered at first only 3 random variables, later it was extended with model uncertainty on both the resistance and the loading side, but here the 3 random variables are the compressive strength of concrete, the yield stress of the rebar, and the loading. These are the distributions we considered, and here we can see some responses which are calculated using the finite element code using different material inputs. And just to show some results, so for this low dimensional case using this response surface based method, we already needed 66 reliability or limit state function evaluations. So in this case, for this model, given these hardware components, 2.5 hours were needed, which is not that bad. It's still quite acceptable. And what is more important for practice especially, so here is a table which compares different modeling approaches. So just going back to this table I mentioned already, if we extend our model in this dimension, considering more advanced mechanical model, which is in this case a nonlinear finite element model, these 4 columns indicate the gain we can get. So here, this first column is the Eurocode-based sort of state of practice approach, just using a Stratton tie model. This is the design value of the resistance we can obtain, and this is the design value of the action. This is set, as you can see, set in a way that with the reliability analysis we achieve sort of 100% utilization. But what is important that we can see here is using a standard, basically hand calculation, the structure doesn't comply. And if we move to these methods, now it's not important, those who are familiar with these methods, so these methods are proposed in the literature, mostly in the reinforced concrete literature. Basically, these are semi-probabilistic safety formats which utilize or which are recommended for nonlinear finite element based resistance evaluation. So this is the ECOV method recommended or proposed by Vladimir Chervenka. This is the global resistance factor method, and this is partial factor based method, which is also recommended for nonlinear finite element analysis. So what we can see, the trend here is that we can basically show that there is a large reserve in the structure, by moving from the Stratton-Time model to the nonlinear finite element model. Here we can see the utilization ratio is decreasing. But it's still larger than 1. And then if we extend our model, not only in this dimension, not only the physical model is more advanced, but the probabilistic model is more advanced, then we can obtain, for this particular case, that the structure complies with the standard. So it appears to be that a large reserve can be uncovered. Another example, which is a continuous beam. This is a real structure located in Portugal. We considered this simplified analysis, just having this three-span structure subjected to traffic load. The dead load was also considered, but the dead load was considered as a deterministic action. And the model consists of beam column elements with embedded rebar, again perfect bond. The nonlinear material properties are again the same, and the failure mechanism is basically a plastic collapse mechanism of this continuous beam. The limit state function is a little bit more complicated. We have 5 random variables. Later on, this example was also extended with more random variables. Now we have additionally the ultimate strength and the ultimate strain of the rebar included. And then here we can see the considered probabilistic models, and again some finite element runs with different input values, considering the mean and sometimes considering the design value of these material properties. And then just as an indication for the computational requirement, so for this example, roughly 120 limit state function evaluations were needed, and the total computational time is 12 hours. So now we are approaching the domain when it's a little bit annoying to wait for the analysis to be completed. And regarding the comparison, so this is a table which is constructed the same way, showing the same methods. So what we see again, that using just an analytical model, just using the static or kinematic theorem of plasticity, if we calculate the resistance of the structure, we cannot, basically the structure doesn't comply. And if we move to a more advanced model, so we take into account the hardening of the rebar and also the more realistic representation of the material model of concrete, we can uncover some reserves, but these are still not sufficient. So we set the model not to be sufficient, and the model or the structure complies only if we do a reliability analysis. And just a note, we are currently extending this model to take into account the corrosion effect. So all these analyses were corresponding to uncorroded structures. So we first would like to consider pitting corrosion, and we are exploring open seas to do the nonlinear finite element analysis, because it offers the opportunity for easy parallelization, and we can utilize the available GPU solvers, and also they also provide Amazon cloud templates to do cloud computing. And just briefly mention these other structures we are considering in case of hydraulic structures. So it's the sheet pile wall. Here the main challenge is that we can have multiple failure modes. The anchor can fail, the sheet pile wall can fail, and the whole structure involving the soil can lose its equilibrium. And this is a lock, which is a reinforced concrete structure member, but here also soil structure interaction plays a role. And just to sum up, I would like to finish with challenges and questions we are facing. During the day, we have already seen a couple of answers, for example, how to use smart algorithms and what we can expect from smart algorithms. But here I just listed what we are considering and planning to do in the future. So incorporation of random fields, multiple failure modes, and also the final step is to translate these analysis results to methods which are applicable by practicing engineers. And then just to open or to close this short presentation with 3 points. So we are, as I mentioned, implementing the methods which are available in the literature, and we are open to actually join our efforts with others, because we are a small group. So we believe that it would be much more advantageous to do these things together, and maybe also to agree on some benchmark problems and to compare these methods how they perform. And also, we would be open also, and then would be happy to have something like a jointly written, compiled document on these methods, and maybe to list that these methods are working for these kind of problems, and these other methods have limitations in these. For example, the limitations what Karl Bleitung just mentioned now. So thank you for your attention.